So now next we want to, find the explicit map between SO3 and SU2. So, but before we do that, we need some properties of Pauli matrices. Okay, so Pauli matrices, they satisfy this anti-commutation relationship. So this means that sigma A, sigma B plus sigma B, sigma A is 2 of delta AB, okay? That's number one. Number two is that they are traceless. Number three is that they are Hermitian. Number four is the commutator of two Pauli matrices is 2 times I epsilon ABC sigma C. Okay. So from here we can find what the trace of two Pauli matrices are, or two Pauli matrices is. Okay, so we know that we can use, say, this relationship. Then I get trace of sigma B, sigma A. So there's a minus sign here, plus 2 delta AB. Okay, now this minus sign, I can factor it out. Trace of sigma B, sigma A, plus 2 delta AB, trace of a 2 by 2 identity matrix. Because AB, these are labels of the matrices. These are not matrix elements. But using the fact that we have the trace is cyclic, so trace of AB is equals to trace of BA. We know that. Using that, we can write the first term as trace of sigma A, sigma B, and the second term 2 times delta AB times 2. So this means that now I can bring this to the other side, and then I have 2 trace of sigma A, sigma B is equal to 4 times delta AB, and therefore trace of sigma A, sigma B is 2 times delta AB. Okay, this is a very useful relationship. Now, if I look at a finite element of SU2, then we can express this as e to the power I. It has 3 parameters. Let's call them theta, vector, dot, t. T being the set of generators, right? And we saw that we can express this as theta divided by 2 dot sigma. So now what we want to do is that we want to explicitly, create a map between, say, a rotation around the z-axis by theta and some u. We want to see, so we know what this rotation is. This rotation is, say, cosine of theta minus sine of theta, sine of theta, cosine of theta 0, 0, 1, 0, 0, right? So now my question is, what is the U that corresponds to it? Of course, there's going to be U and minus U as well. But if you have U, we have minus U. So that's not a problem. Okay? So to see this, we know that we can always build up like a finite rotation from kind of a series of small infinitesimal rotations, right? So let's see if we can use that to our advantage. So x of r prime is equal to, say, r prime of a, sigma a, and that is equal to u x of r u dagger. But r prime a can be written as the matrix R acting on R of B times. So here we are repeated indices mean that there's a sum. So this is the left side. The right side is U x of R U dagger. Is this clear what I'm doing?
Yes, sir.
Okay. Now we are going to assume that our rotation is something very small. Okay. Before we do that, let's write the right-hand side explicitly as well. So we have RAB, RB, sigma A is equal to U. Here I have, say, I should not write the hat when I'm writing the vector, the component. Okay. So here I have R of B sigma B U dagger. Okay. So I'm just like writing this out explicitly. But R is some arbitrary vector. So for this equation to be correct, it has to be correct for all R's. So I can write this as this implies R of AB sigma of A is equal to U sigma B U dagger. Okay. R is just some coefficient that I get rid of from both sides. So now what I do is that I consider small rotations. If I have a small rotation, then the left-hand side is delta AB, the identity matrix, plus I'm going to choose my my generators for R3 to be Hermitian and complex. So I'm going to introduce an I here. And theta is the rotation. And I'm doing a rotation around the third axis, so it'll be T3. So this is this object. And then I have, let me just, what I will do is that instead of writing as delta, I'm writing it as the identity matrix. And this whole thing is a matrix, so I'm going to put the index AB here. And that multiplies the Pauli matrix sigma A. So this is the left-hand side. For the right-hand side, I'm going to assume that this also, we are going to only express this as linear order in theta. Okay, so because you will have some expansion theta, we just don't know what this T is. It's going to be T3, but we don't know that yet. Or tau 3, I should say. Let me just use, because I'm using T as a generator of R, let me use a different symbol for the generators of, let's call this tau. Okay. So on the right-hand side, I'm going to get some identity matrix and then plus I of theta times tau. And then I get sigma b, and here I will get 1 minus I of theta tau. Yeah, sorry, the tau will be just one matrix because I've got just one theta here. Okay, is this clear what's happening here? I think you're a bit lost probably because of, let me just remind you, we are looking for u, that is a rotation around by angle theta that corresponds to a rotation around the z-axis in physical space, and that will have some form of I theta tau. We just don't know what tau is. We want to find out what tau is when the rotation is in physical space by theta and around z-axis, okay? We're assuming that the same angle that parameterizes our rotation in physical space is going to be the same angle here, which is a valid assumption. And then what we're doing is that we're expanding both r, the rotation in physical space, as well as u, as in terms of infinitesimal parameter theta. And we're going to keep the linear terms on both sides, okay? So I'm going to pause here in case people are confused and people want me to have some questions.
What is T3?
T3, oh yeah, very good. So here I wrote R of Z, right? So R of Z is, we can write it as e to the power I theta T3. T3 is the generator of rotation around the z-axis. So explicitly, T3 is going to be this thing. T3 will be 0 minus I 0, 0, 0, 0, 0, 0. Okay. So when you exponentiate this, you should get to this matrix. If you plug that in. Okay.
I got it.
So this is just the infinitesimal version of this. So now if I expand this, I'm just going to erase this. So if I expand this, what will happen is that the first identity will be, they'll cancel out from both sides. On the left side, I'll have I theta T3 AB sigma A. On the right-hand side, I will have I theta, the commutator of tau and sigma B. Okay. And then, we can also get rid of these guys. So we have, in the end, we have T3 AB sigma A is equal to tau sigma B. Okay. Now, what is tau? Tau will be some linear combination of the sigma matrices. because that's the most general generator we can have. Okay, so if I do this, then I can write this as alpha A, sigma B. Now what I can do is that I can then multiply both sides. I have to be a bit careful here. Let's see. Yeah. So I can multiply both sides now by sigma C, sigma A, and I can take the trace.
Sir, why is C on the left-hand side? Sigma C.
So I'm multiplying both with sigma C.
Yeah, but sigma shouldn't be in the right side. Like we can put something in the middle, I guess.
No, this is just a matrix element. This is not a matrix.
Oh, okay.
Yeah. Okay. So here we have 2 times delta AC. On the right-hand side, I have alpha A, trace of sigma C, and now I will have 2 times I epsilon AB, D, sigma D. So here on the left side, I get 2 T3 C of B. I'm summing over the repeated index here. On the right-hand side, I have 2I alpha A epsilon A B D, and the trace of sigma C sigma D is going to give me 2 delta C of D. So I can cancel some stuff, and then I have I alpha A, and then there's a 2 here coming from here, and CD, if I sum over that, then I have epsilon A B C on the left side. On the right side, I have T3 C of B. And now what I can do is that I can say, then I can, so I see that there's a C and B are free indices. So I can use the fact that if I have epsilon A, B, C, and I contracted it with epsilon, say, D, B, C, so this is summed over, that this is actually factorial 2 delta AD. Okay, proving this would be a separate exercise. So if I do this and then I multiply both sides by this object and do the sum, then what I'll have is that I will have, there'll be a factorial of 2 coming from here. So there'll be a factor of 4. And I can bring that factor of 4 over into this side. So over here, I'll have T of 3, CB epsilon DBC. On the right-hand side, I will have, because of the delta, I will have just, I think there should be a fact, there'll be an I times alpha D. Okay. Now I know what the structure of T is. T is T3 of CB is given by I times epsilon 3 CD. Okay. If I go back to T3, you see that this is that it's only non-zero when the row and column are 1 and 2, right? And the sign flips. So okay, there's some I here. Okay. So this is basically T3. So if I now plug this expression of T3 in this equation, then I get 1/4 of I epsilon 3 CD epsilon D BC, and that's going to be equal to I alpha D. Let me make sure that so this should be CB. Okay, not CD, CB. Okay, CB. So here I have the i's canceling out, and here I have 1/4. I'm missing, and because there's a sum over 2 indices, I'll get a factorial of 2 here, and I'll get a delta 3D, alpha D, which gives us that alpha D is alpha 3 over 2, which tells us that the rotation around the z-axis, so rotation by an angle theta around the z-axis corresponds to e to the power I theta by 2 sigma 3. So I think I messed it up a little bit in terms of introducing alpha. I think the alpha itself could have been the theta. So if I go back and fix that, then what's important here is just the fact that the rotation around the z-axis gives us sigma 3 over here. Okay. So I made some, a poor choice in terms of parameterizing tau. I actually didn't need the theta here. Or maybe I did. Yeah. Actually, no. I think I did everything right. This is what everything is right. Yeah. What this equation tells me is that alpha 3 is half. Yeah. So then everything is fine. Okay. So similarly, you can show that if you do a rotation around the x-axis by angle theta, that corresponds to e to the power I theta by 2 sigma 1. If you do a rotation around the y-axis by angle theta, that corresponds to e to the power I theta by 2 sigma 2. Now, before I go, I just want to point something weird out. So if theta goes from 0 to 2 pi, then r of theta goes to r of theta, right? So, I mean, if, okay, what I mean is this. So we have theta here. Now, if I change theta by 2 pi, so if I take theta to theta plus 2 pi, that's what I mean, then r of theta goes to r of theta, right? But e of I, theta t3, by 2, that goes to minus E of I theta T3 by 2 because of this factor of half. So even though in physical space you rotate by 360 degrees, on the Hilbert space, you don't come back to the same point. You come back to the negative of the vector. Okay, and that's related to fermionic statistics.
So does that also explain the double covering property? That
Exactly. Yeah, that's related to the double covering property. Okay. So anyway, I think this has been quite an intense class. Before I take questions, let me just give you your attendance quickly, and then I'll take some questions, okay? But I'm here for some questions and answers.
Is this the phenomena where you rotate the electron 2 times before it comes back to the same spin or something like that?
Exactly, and this is related to the Fermi statistics.
Yeah, I see.
You can show for 2 fermion systems, there exists a particular state in which if you do a rotation of the system which involves switching of these 2 particles, then you get essentially the wave function but with a minus sign. Okay, so this is related to yeah. So all of this is like there's a deep group theoretic structure to all of this.